welcome everyone. So we started AllegroGraph around 7 years ago, and because I had looked at RDF, I thought RDF is all about graph databases, so that's why we gave the name AllegroGraph. But then recently we got these non-RDF graph databases coming up, and people would talk to us and say, hey, well, but you guys, you know, AllegroGraph is not really a graph database because it doesn't do property graphs. Well, I was a little bit confused that we had given our database the wrong name, but I decided to look a little bit closer, and then I actually discovered that we were already working with property graphs for many years. And so this is kind of a combination of 2 or 3 talks that I recently gave about property graphs in AllegroGraph. And I'll give you 3 examples of how we work with property graphs in AllegroGraph. First is in the fraud detection, and I've given this demo before, but I'll focus this time only about the property graph aspects. Then some people in the semantic community are looking at the phenomenon of bi-temporality. And again, bi-temporality can be solved in triple stores by using property graphs, or the 4th element of a triple. So I'm going to give a little bit of a demonstration or talk about that. And then finally, we can also use the triple-ids of triples to create property graphs. Yeah, and actually we can then even show it in graph. I think it's fairly unique that we can have a graph where we have reification and property graphs and show that in a visual display. So okay, let me start. So let me start with fraud detection. Yeah, so I gave this talk in San Jose at the NoSQL conference. So I used an example where I said, okay, so now imagine you have a database with accounts of an online bank, and you have payments between accounts, and say you will try to find a circle of payments between accounts that all happened within 10 miles of San Jose within the last day, and where the payment was more than $1,000. I mean, this is a real case that we work on. Now, for people who don't know what property graphs are a technique, well, a graph where both nodes and links can have properties. So if you look at this, you can see it says 4 parties that pay each other. Each of these nodes is an account with an email and an account number, etc. What you really would want is also to say something about the paid relationship. Yeah. So here comes the property graph element in, where you can say, well, this paid relationship was about an amount of $2,000. Here was the lat long where it happened, and this was the time when it happened. Yeah. So now, if you want to do queries where you use property graphs, and you try this in a normal graph database, then I can assure you it won't be particularly fast. So I actually invite you to try that for yourself. But we solved it in RDF, and it's pretty fast. So what do? Say we have a number of accounts, yeah, that pay each other. Then how we represent this, that we say subject account A pays an account B, and then we use the 4th element of a triple to hang up other properties off. So in this case you see G1, so here I could say that G1 happened at a particular time, had a particular level long when it happened, and a certain amount. Yeah. So now we implemented property graphs using the 4th element of the triple. And then we can use that in SPARQL. Yeah, so I can say, well, there was a payment from A to B, and as the 4th element we used pay 1, and then from B to C, C to D, and D to A. Yeah, and so now we have a circle, but we also have the 4th element of each of these triples, and then we can do filters on this. We can look at the time, we can look at the location, and then ultimately we can say whether something happened in a particular duration and within a particular time interval. And in a particular geospatial region. Yeah. So the full power of SPARQL, and you can do everything you can do with the triple store. So let me just give you a demo, a quick demo of our data. So let me go here, and I think And then we have it running. So why doesn't it want to get bigger? Here it is. So let me open a database about fraud. Yeah, let me get a particular user that I know is in the database. So there's a person called bruce.rosie@hitachi.com. Yeah. And if I click on this person, then I see the account for Bruce Rosie. So I see an account date time, an account IP address, account number. I see that this account was opened in a city called Gun Barrel City. So actually, if I click on this, you are in the geo names database where we have meta information about cities. So here you see that it was in Texas. You see there's about 5,000 people living there, latitude, longitude, etc., etc. And then what you see is we have a paid relationship. So we see that Bruce Rosie paid Clarence Duran, yeah, a particular amount. And you don't see the value, but actually what you see here on the right is the name of the graph in which things happened. So let me go to so you see these numbers here, which are the fourth element of the triples. Now let's look at some of the payments. So here we see that Clarence is the receiver of a particular transaction of $254. Now when you see my mouse is on top of the dollar amount, but at the bottom you actually see the event that happened. So this is the meta information about this payment relationship. And when I go here, I see a certain amount, the time when it happened, where the payment happened, and who the sender was. Yeah. So we have amounts and we have payments between two accounts. So I can go back here and I can explore this graph on the screen by using sender, receiver, and sender relationships. So I could look do this, and I could look at this, and I could go forward, and let's just take a few interactions, and then at some point we'll have a circle that's filled up. And anyway, you can imagine that we have, so what you see here is that we have accounts, and these little ones are the transactions, and we looked at the amounts of these transactions, and then based on the amounts we gave them different types. So you could have medium, large payments, or normal payments, very small payments. But it's kind of hard to see how money goes from one person to the other if you have a little object in between. So if I go back, then I can also go back to my predicates and say, I don't want to look at receiver and sender relationships. I just want to look at the payment relationships between them. So when I do this, now when I look at this, I can, and I look at this, and then I got a little bit of a weird example here, but now I look at the graph just by the paid relationships, but the payments are just all one color. So one of the things I even did is when I go back again, I said I don't want to look at these paid relationships. I even could take these predicates and give them special types. Yeah. And now when I look at it, I see the different colors for the payment, and I could keep going and find the relationships between those. And again, it's not very important that I go into this here. But I hope that you see how I can use the fourth element of the graph, yeah, to say things about a particular relationship. So this was my first demo. Any questions so far? All right. So then the second example I want to talk about is Bi-Temporality. Now, if people work with relational databases and they do a lot of temporal work with databases, then they might know about this phenomenon. But most people are kind of unfamiliar with it. The Wikipedia has a reasonably good explanation of what temporal databases do and what bitemporality is. The core of bitemporality is that You might have a fact that there's a certain valid time, so something is true from the start point to an end point. But there's also a transaction time when you record that something is true. And when you work with the temporal data, you combine both the valid time and the transaction time. Yeah? So this is a little bit abstract, so let's look at where is this important? Well, it's important in intelligence agencies. Yeah? When did we think that a person was where during what time interval? And what happened to inferences made based on earlier incorrect knowledge? So this is one area where this is important. Or you might look at the medical domain. Here we had a patient with a spell of dizziness during the last 6 months, so we proposed treatment X. Now we know that he had it only for the last 2 weeks. So what do we do about the treatment? Or financial, we could say, so we have 2 overlapping loans. Others recorded at different times. Which one was true at the moment of accepting a loan? So these are all kind of things that people in the real world have to deal with when they deal with time. There's a really good overview paper by a company called Capgemini that wrote this report, Enhancing Time Series Data by Applying Bi-Temporality, with this great title. It's not just what you know, it's also when you know it. So I would recommend that you find this thing on Google. But let me go a little bit deeper for the nerds in the audience. Yeah, how do we deal with bi-temporality in a triple store, and how do we use property graphs? Yeah? So say I want to add some facts about where a person works. Who a person works for what department in an HR database. Now I can add some bi-temporal facts like person 1 worked in January and February for Department 1, which is the black one, and then he worked in March and April for Department 2, and we recorded both these facts on the 1st of January 2013. But then later, we figured out that we made a mistake, and we put in the database that this person actually works in February and March for Department 1. Yeah? So now, in a company where you can work only for one department at a time, we have a problem. Yeah, because here the database is inconsistent. So how would you even find this inconsistency in the database? Well, you can do this with 2 representations. The first one would again be a property graph. So you would say person 1 works for department 1, and the 4th element of the triple would be statement 1. And then you would say, well, statement 1 is a start point T1, end point T3, and the recording time was T100. And then we would say person 1 works for department 2 at statement 2, where the start point was T3, end point T5, and the recording time was the same time as here. But we also added the statement that this statement is currently true. Yeah? It's very important to remember that we take a little bit of pain when we add these facts to the database and do a little bit of processing to make sure that we always know what the most current truth is about a certain matter. And why this is important, I'll talk about it later. Then here we get the conflicting statement where we say that the person actually worked from T2 4. Now this is representing this data using property graphs. You could do the same thing with events, how we usually do things. We have events of type work for, the actor is person 1, and where is department 1, and then the same things that you saw above. But for now, let's just focus on the top part. Yeah? So the first thing that I just said is that you saw that some of these statements had the feature that, the property graph had the feature that it was the current statements. And why that is important is, well, we were working with some customer databases where you had many statements, many statements about something recorded at different times. Then you could get, when you did the queries, you had to always look up what is the most recent belief that we have about what is true. And so we have to do SPARQL queries where we say, well, find the graph where person 1 works for department 1 and works for department 2, and they're not the same. And then we wanted to know, okay, but which one is the last time, when we knew about it? So we had to do a subquery here, a subquery there, and then we had to do a long filter expression to figure out whether there was an overlap. So what we did is we add a little bit of magic. So this is again the same thing. We find the 2 graphs. If something is true, we take filter. And now it looks a little bit prettier here. let me secure here. Oh, sorry, this was wrong. Look here how in this particular frame we have to look at the particular graphs, and then we have to look up the start points. Yeah, so that's a lot of work. So what we can do is we have temporal predicates in SPARQL, and this is magic predicate here. So we can say now we don't have to look at all these things here to figure out when the dates were active. We can just say did graph 1 and graph 2 overlap. Yeah? So now it's starting to become more readable. That can be even more readable if we use another magic predicate that we're going to introduce in the product, which is current. So we say, give me the most current statements for this, give me the most current statement for this statement, and then is there a temporal overlap between the two? And now you kind of have a chance of understanding what the query is about. Yeah. So that was the second example of using hypergraphs, and then the third one is using triple IDs for property and hypergraphs. And so in AllegroGraph, you have like any quad stored subject, the predicate object in the graph, but we also make the triple ID available, and we actually can serialize and write out triples with the time interval. So we make triple ID, of course we realize it's not entirely RDF, but it's a very, very handy feature. Yeah? So say I want to do a property graph with triple IDs. Say I want to do the statement, Jan's wife says that he is 100 kilos. If you use the typical W3C standard verification, then you would say, well, there's a statement, a type statement, and the statement has a subject, Jan's predicate weighs, and object 100, and then the creator of the statement was his wife. Yeah? So we need about 5 statements to interpret this sentence here. Now, if you do the same statement with the graph, then you could say Jan's weighs 100, statement 1, DC creator, his wife. And this is, of course, what I've been showing in the first 2 examples. But some people really hated that they have to give up the 4th element to do provenance or verification. So for those people, say use the triple ID. So now I can say Jan's weighs 100, and this is triple 1, so we can say triple 1 says the creator, his wife. So now you still can use the graph element for something else, and use the triple ID. And you can actually, and so here's one of the things. Many people say, well, I like this idea, but when I send my files to other people, I still want to be able to use the standard W3C way of verification. So in SPARQL, you can actually take fully W3C reified statements, read them in with this SPARQL statement, and kind of delete the original statements, and then insert it like this. You find the ID for a particular subject, predicate, object, and then you say ID has the property, and then whatever you want to say about it. Yeah, all the things you want to say about an object. And then you can also do queries using the triple ID. So say I say that Gary is a person and Gary likes cats. Yeah, say I load this in the Triple Store. Then I can execute this query. I can say, well, insert Jan's beliefs ID where the ID of triple ID, and then where, no, sorry, let me start again. Say you added this to the Triple Store. Yeah. Then you can say something about the triple ID of this particular triple by saying ID, and then this is the magic function that will find the triple ID for who likes a particular thing. Yeah? And then when you finally print it out, you see that it's, then we took the triple ID and put it into a normal triple. Now we also can write functions where actually if you really want to exchange your data in traditional W3C notation, then you could do that and write it out as the full triples again. And then finally, how does it look like in graph when you do this verification? Well, we have one customer who's going to write a blog about it, so I'm going to keep this extremely short for now. But he does natural language processing with a lot of, and uses a lot of temporal concepts. And so he can, for example, do a sentence like, this morning Jim planned on going to Costco before 6. Yeah? And he would take this sentence and parse it. So he would have a planning event about a particular morning. This is the activity and where he wants to go and when he wants to do this. Yeah, so these things would be the interpretation of the sentence, but there are multiple interpretations of this sentence, and they all revolve around Jim and about Costco, and so before you know it, these graphs all intermingle. So one technique to keep the interpretation separate is to make meta statements that link them all together. So these blue lines basically hold this interpretation together. Yeah? But note that if you're familiar with graph, that you probably have never seen it before, that the nodes can also link to the predicates or the links between them. Yeah, and now of course you can, for example, say, well, you say you have multiple interpretations of this sentence, then you could put meta information on this conjunction, and you probably, for example, could say, well, I believe that the interpretation is true. Yeah. So now I use meta information and added that to this particular verification statement. Okay, and with that I end this presentation, and I would like to see what the questions are so far. The first question is bi-temporality part of a standard? No, it's not. I mean, well, Oracle and DB2 have ways to do it in relational database schemas, but I know that a few triple store vendors are working with banks that all ask them for a standard way to deal with bi-temporality, so I expect at some point we'll have a kind of a standard. Is it expensive to compute? No, it's not more expensive than any other graph query. I mean, you might remember, or you might know that in the semantic world, working with graphs in SPARQL is now just a commonly accepted feature, and our query engines are now all able to deal with it in the most efficient way, so it's not inefficient in any particular way that I know of. Do you have similar operators for geographical operators? I don't know exactly what a query refers to, but if you were referring to the magic predicate, then I actually would suggest then you go to the France website and then you Google for France documentation. Is it magic predicates? I think you might magic. Oh, magic properties. Okay. So here are our magic properties for geospatial, social network analytics, and temporal. Yeah. So here are a lot of different geospatial magic properties. I'm kind of thinking that you were referring to that things like you say the subject is in the bounding box given a particular location in the lower left point and the super right point. Okay. Can I create my own magic predicates in AllegroGraph? That is a very good question, and we get that question more and more often. So right now it's usually something that we do for customers, but in the near future we'll make something where you can do those things yourself, and you write your functions in JavaScript or in whatever you want to write it in. Yeah. Magic property, is that part of the W3C spec? Yeah, it's kind of a spin. Is I think spin is one proposal for W3C where we have this concept of computed properties. And by the way, the syntax is 100% SPARQL. Yeah. The semantics is just, well, something else. It's a computed entity. Yeah. How scalable is this? It's, I mean, as I said before, I think we have this question before. It's just dealing with graphs in SPARQL queries is just as efficient as anything else in SPARQL. And so it's not more or less scalable than anything else. Why do graph database people say that triple stores can't do property graphs? I have no idea. I hope I showed today that we can do property graphs. All right. Okay. Thank you very much for your time and for listening.